is actual yield over theoretical yield times 100%, which means that in the end you will be left with something that is a percent value. So what are these two things? The theoretical yield is really what we've been doing so far, okay, which is also the stoichiometric spelling. Stoichiometry, whatever you calculate, that is what your theoretical yield will be, because in an ideal situation, that is what you should get, okay? If you look at the calculations that you had, or even for this sheet, okay, that you were working on, so question number 2, it says how many grams of sodium fluoride are required to form the 485 grams of sulfur tetrafluoride. 485 grams here is a theoretical yield, okay, that's what you're supposed to make. Or if you want to look at the questions we were doing before for ammonia, this is what you're supposed to get, theoretically, ideally, everything in a perfect world. But we don't live in a perfect world, right? Things don't happen like that, okay, for most cases. So which means we are stuck with something that is called an actual yield, okay? So you go in the lab, you start doing the work, and after you're done isolating your product, it turns out that you get something a little bit less, okay, or more, all right? And if you just think about your separation lab also that you did, some of you got less than 100% after separating the 3 components in there, some of you got more. Am I right? Did anyone get exact 100% back? Even if you got 100% back, okay, remember we had a specific mixture in there, 5% iodine and whatever 45% sand. Did you get exactly those quantities? No, okay, and that doesn't happen. So that is what we call the actual yields then, okay, that when you go in the lab and you start working, you end up getting actual yields, okay, and some of you got a little bit more than what you should have gotten because you had a lot of water in it, right? Okay, yeah, a lot of things were not quite dry, all right, so that's kind of what happens. So in any case, the actual yield depends completely on your technique, okay, when you're working with everything. So let me go back to your problem that we did for ammonia. How much ammonia in gram is produced when 3.2 grams of nitrogen is used? That was one of the problems I did for you last time, okay? And the answer we got was 3.88 grams. Ammonia from 3.20 grams of nitrogen. Do you remember this problem? Look back in your notes, okay? So this is what we got, and this is called the theoretical yield or the stoichiometric yield, okay? Because if everything works fine, this is what you should get, okay, in there. And then you go in the lab, you do the process, you do the reaction, and it turns out that maybe you end up getting something like 2.98 grams as your actual yield. And by the way, you're most welcome to use, what do you call? Shorthand. AYTY, theoretical yield, actual yield. Okay, if you want to for this. So if your actual yield turns out to be 2.98 grams of ammonia, after you do the same reaction that we talked about, then our percent yield, okay, is going to be 2.98 divided by 3.88 times 100%. Put the units on so that you know that you're working in the same units, but if you are, it honestly doesn't matter, it's going to cross out. The only thing is that you should not have grams over kilograms or something like that. Okay, make sure that your units are the same for everything. So let's go ahead and do that calculation. I don't have that because I have it for something else. So 2.98 divided by 3.88. 76.8%, right. when we do reactions in lab, you publish them, okay? They go out there for everybody to do, okay? So you did this wonderful synthesis of ammonia. Now you know, you want the world to know about this, okay? So you publish your work, and then you post it on there that, of course, you wrote there and say you have 76.8% yield, okay, for this reaction. If you do this, and I go into the lab, and I do this reaction, I should get about the same, okay? That's how I know that your reaction was good, okay? Because if somebody is able to repeat those things, then it works. If I end up getting something like 92% yield, that means there was something wrong with your technique, or I need to repeat it again, okay, and see what happened. Because technically, if you do the same reaction, you should also get the same percent yield, okay, just about. So something is wrong somewhere, okay, if you don't get the same kind of percent yields. But there's another thing that percent yields tells you. This is not 100%, right? Which means this was not an ideal solution. How much did we lose here? About 23%, right? We lost about 23% of our product somewhere, okay? So if you lost 23% of your product somewhere, who's paying for that? Right? Somebody's paying for it. Okay, so first of all, your process is not efficient. Second of all, you're getting less product. Third of all, you're still paying for the 100%, okay, in there. So which means that processes should be efficient, all right? And just as a side note, you may be interested, I don't know if you're interested in medicinal chemistry at all or not, but in medicinal chemistry, this is one of the biggest problems that they have, because they have to take a drug from the lab to the public. And once you go from lab into industry, then you have to upscale everything, okay? So from working with small grams to kilograms, and if the percent yield is not translated into large quantities, then industries have to work differently, okay? And so the processes that we use in the lab are not necessarily the processes they use in the industry for manufacturing anything, okay? But that's one of the reasons that you have the cost of the drugs that you have also, okay? The starting materials is of course one thing, but it's also the efficiency of the reactions. A lot of industries would like their efficiencies to be 99% if possible, okay? But sometimes that's not possible. One of the most interesting syntheses that came out in the last 20 years was for Taxol, which is used to treat breast cancer, okay? And it was a natural product that's gotten from a tree. So you can extract it from a tree, or you can make it in a lab. So it took about 15-20 years for scientists to actually make it in the lab, okay? And once you make it, then you don't have to kill trees anymore, okay? So that's the upside to it, if you can make it. And it turns out that the yield was merely 5%. After 20 years of slogging off in the lab and doing so much work, in 20 years, I'm just hypothetically saying, I think it's anywhere from 15 to 20 years. It took them a long time to do the synthesis of Taxol, which if you don't know the structure of Taxol, go ahead and Google it today. It's a huge molecule, and so once they synthesized it and the yield came out to be 5%, who's ever going to make that drug? Okay, never. So which means that you still have to use natural products to make that drug. Okay, on the other hand, aspirin also is obtained from a tree, but now aspirin has a great synthesis, so you don't have to take it from trees anymore. Okay, so it depends. If you can do the synthesis properly with a good yield, then it's a good thing. Okay, 76% is not that bad. Okay, at least for us in the labs, it's not bad. Usually we try to do something in 80% or above yield. Okay, that works out good. There's one lab that you're going to do in another week or so, which is the synthesis of alum. Okay, that's coming up in 2 weeks or so. And that has to do with your synthesis, okay? Because you will take aluminum and you will make alum from it. So it's a nice synthesis, okay? And in that case, you will see how good your efficiency is, because when you go and filter your crystals, you will see that maybe somebody else in the lab got tons of crystals, and you just have the ATBT crystals, and you're like, what the heck did I do over here? Okay, that I got such less ones, and So it's a lot of it is dependent on your technique, how you do stuff. Okay. So that's percent yield, and your next few questions in here are percent yield, but before we start doing this, I need to talk about one last thing in this chapter, and that is limiting reagents. We can go back to making sandwiches if you want to, okay, if you want to think about that. But it's almost like, if you're making sandwiches and you did want tomatoes on there, and you have still some bread left, but you don't have any tomatoes left, then you're not going to make that sandwich. Okay, so which means that tomatoes become your limiting reagent. All right, so even though you have everything else in there, if you don't have tomatoes in there, and you really want tomatoes, okay, then that is your limiting reagent, okay, in there. Definitely if you don't have bread, that definitely is a limiting reagent, okay, because there's no sandwich without a bread. So that's what limiting reagents are. So if you have 2 or 3 things in a reaction, then you have to account for everything, okay. So let me write a reaction here. It's a different one from what you've done before, just to give you good practice. So here is ozone, O3, and nitrogen monoxide to give you oxygen plus nitrogen dioxide. So the question is, how many grams of nitrogen dioxide, and I'm going to write this problem right on the equation, okay, so I don't have to write the words, right, because it does take a little bit time, so I'm going to read it and just follow it through. So how many grams of nitrogen dioxide are produced when you have 0.670 grams of nitrogen monoxide and 2.90 grams of ozone? That's our first question, is how many grams of nitrogen dioxide are formed, okay? So the next question will be then, what is the percent yield? We're going to do everything, okay, in this one. So what is the percent yield if 0.70 grams of nitrogen dioxide are produced? And the third question in this one is going to be, calculate the excess reagent left. If you can do a problem like this in stoichiometry, you've mastered stoichiometry, that's it, okay? Because these are the 3 questions that are possible in any kind of stoichiometric problem, okay? Is how much product is being produced, or how much reactant is being used, what is the percent yield, and then of course the excess reagents, okay, if you have a limiting reagent problem. So first of all, how do you know it's a limiting reagent problem? Because we've done stoichiometry before, okay, where you had the same kind of thing is, okay, how much of nitrogen dioxide is produced if you had 2.90 grams of ozone. Maybe that's what you had before. But now what's given to you is 2 quantities, all right? Previously what was given to you was only 1 quantity. So if you had only 1 quantity given, and if you can look back in your problems that we did, you only had 1 number given to you before, okay? But if you have both the quantities given for your starting material, that will tell you that you have a limiting reagent problem, okay? So which means that you're going to approach the problem slightly differently. Now you're going to have to calculate for both, okay? Not just one, you're going to have to calculate for both. So let's start with part 1. Okay, where we'll start from 2.90 gram ozone. You can start from nitrogen monoxide, whichever one you want, it doesn't matter. So ozone and then nitrogen monoxide. We're going to have to work with both. So the setup is the same, okay, which means that you're going to convert grams to moles, and then you're going to do mole ratio, okay? That's where we're going to stop, at the mole ratio, because we have to do something before we go on to the grams of the product, okay? You can go on to the grams of the product, that just takes a little bit more time, okay? So then 2.90 grams of ozone times, and then we're converting this to moles, so grams of ozone to moles of ozone. Our mole ratio is moles of ozone to moles of nitrogen dioxide. I didn't even ask you, is the equation balanced? 4 oxygens, yes, we're balanced. Okay, that's good. Aren't we lucky? All right. And aren't we lucky everything is 1:1? Yeah. Okay, so 1 mole of ozone has 47.97 grams of ozone, and then the mole ratio here is 1:1. Okay, and the answer here is 0.06045 moles. And then I'll set up the same thing for nitrogen monoxide, so 0.670 grams nitrogen monoxide times, and I convert it from grams to moles. My mole ratio is still going to be for nitrogen dioxide because that's my product, that's what I'm trying to make. So now moles of nitrogen monoxide, moles of nitrogen dioxide, and 1 mole of NO has 29.996 grams here, 1 to 1 here, and 0.0223 moles. First question to you. Are we all okay with this? Yes? So far? This is what we did last time, okay? The only thing we're doing now is because we have 2 reactants, is we are using both of those, okay, instead of just one. But the setup is the same. So you bring it to the mole ratio. Make sure you bring it to the mole ratio, okay? Don't leave it just at moles, okay? Don't just leave it at moles. Bring it up to mole ratio and stop over here, and then compare these 2 numbers. Whatever gives you the smaller quantity of the product is your limiting reagent, okay? Because once this quantity is over, then the reaction cannot go on, okay? So that's your limiting reagent. So after 0.0223 moles of nitrogen dioxide are formed, at that point, nitrogen monoxide is finished. It's consumed completely. Okay, so if it's finished, ozone can just sit there and not do anything at all. Okay, so what's my excess reagent?
EO3 ozone.
The ozone then. Okay, so this is my limiting reagent. Nitrogen monoxide is my limiting reagent, and this is my excess reagent. And if you really want to go shorthand, then it is excess reagent. I don't know. That's just my shorthand. Good? Now that you know which is the limiting reagent, which will give you the smaller quantity, from here you can calculate the grams, okay, that you will need. So now there is just one little calculation to do, and that is convert the moles of nitrogen dioxide to grams of nitrogen dioxide. And this one is 1 mole is 45.9867 grams of nitrogen dioxide to give us 1.026 grams, which is equivalent to 1.03 grams if I get the right sequence. I really urge you, I request you, so from the bottom of my heart, please do not round off anywhere in the middle, okay? Your numbers will come out approximately the same, but not exactly the same, all right? And this is science. You want it to be exactly the same. You don't want it to be roundabout the same, okay? So please make sure that you don't round off anything over here or here until you have the final answer, okay? Then you can round off to the correct significant figures, okay? But other than that, please do not round off. And at the last thing over here, you must round off to the right significant figures, okay? So please make sure of that. I have seen calculations happen and then everything is working fine, and then all of a sudden I see this huge rounding off where you drop off the 0.02 or 0.03. Okay, so the second decimal place, even if you drop that off sometimes, it makes a difference, okay, in your calculation. So please be careful, don't round off. Are we okay so far? Okay, yes, Jeff.
How did you find the excess and limiting?
The excess and the limiting depends on these numbers over here. So this is the smaller number of moles of the product that are being formed. So which means that after this many moles of nitrogen dioxide are formed, my nitrogen monoxide is finished, right? Yeah, okay. So then my second question is about percent yield right here. So what is the percent yield if 0.70 grams of nitrogen dioxide are produced? Don't wait for me for this one because this is easy one. This that we calculated here is the Theoretical or actual yield?
Theoretical yield.
Theoretical yield. Theoretical mean ideal. Okay, this is what it should be. This is the actual yield. This is R produced, so this is the actual yield. This is theoretical yield. So 0.70 divided by 1.03. And here's a little hint for you, is that your actual yield will always be smaller than your theoretical yield, okay? It's very rare that the actual yield is more than 100%, okay? Even for those of you in the lab who got more than 100% recovery, I don't know if you remember me calling you God, you can't forget that, okay? But I know there was a lot of water in there, okay? But in chemical labs, when you do reactions, it's just not gonna happen, okay? If you get more than 100%, again, you did something wrong in the lab, it's not that the reaction is gonna give you more than 100%, okay? It's just not possible. So then this one is 68%. Good? Last question. Calculate the excess reagent left. It's not all that tricky. You just have to make sure you keep your numbers straight. First of all, you know your excess reagent is ozone. Okay, that's your excess reagent. You're going to start from here. Okay, this is where you start from. Your moles of nitrogen dioxide formed are this for the limiting reagent and 0.06045 for the excess reagent. Okay, which means that this is the amount of product that's formed. Good? Okay, that's where you start from these two numbers. So what you will do is you will subtract 0.06045 minus 0.0223 moles of NO2. You'll subtract the smaller quantity because that's how much has already been made. If that's already made, we're done with that. Okay, so whatever is left behind then, 0.03815 moles of NO2, and it's not like you have any of this left behind. You don't. This is how much more you could have made if you had more of the NO, of the nitrogen monoxide. Okay, you could have made more of it. So this is the moles that's left. Now what we're going to do is work our way backward, okay? Because now this is the product. So I'm going to take the same thing, but I'm going to work backward, okay, to get to ozone. Okay, because ozone is my excess reagent. So that's the excess that I produced of NO2, or I would have hypothetically produced more of. So now I'm going to take all of this and just reverse everything, okay? So 0.03815 moles of NO2 times, and now the mole ratio will be ozone to nitrogen dioxide, because ozone is my excess reagent, okay? And then of course it would be moles of ozone to grams of ozone. So this is just doing the backward stoichiometry. The key thing is subtraction over here. So fill in the numbers. 1:1 is the mole ratio, and then 47.97 grams of ozone and 1 mole of ozone. 1.83 grams of ozone. How do you know if your answer is correct? Your number should be smaller than this, okay? If your answer is coming larger than what you started with for ozone, then you're on the wrong side. Somewhere you did something wrong.
Why do you use 47.97 for grams of ozone?
Because I'm converting grams.
When it's calculated, it's not 97, it's 99.
99?
Yeah, it's 99.8.
Oh, is it maybe my periodic table was giving me 97?
Oh yeah, because it ends up
Okay.
at 99.8.
Okay, all right.
But does it matter?
No, hopefully it should not matter. The 0.01 should not, 0.03 sometimes
Okay.
does. Okay, yeah. Hopefully not.
But if it's like, okay.
Yeah. Are we good? Yes? Okay. So the key thing again over here for calculating the excess reagent is the subtraction. Once you get the subtraction and you have the excess moles left, then you just work your way backward, okay, to find out the grams of ozone. Are we good? Okay.